In the last class, we have started the approximating the solution of initial value problem of with the first order differential equation, and we have seen the existence and uniqueness of the solution for the given problem, and also we have derived one method which is very popular named as Euler's method by using Taylor's approximation of the solution at point xn. Okay, so just a quick summary is so you have been given with y dash equals to f of xy with x lies in the interval a to b, and with the initial condition y at x naught is, that is a, is y naught, and we have divided the interval ab into a partition which is a equals to x naught less than x1 and so on till xn with equidistant points. So equidistant, these points are equidistant, and we have general form of xi is given by a plus ih, where I is running from 0 to n. Then Euler's method was given by yk plus 1 is equals to yk plus h9 f of xk comma yk. So what these notations are stands for? So yk plus 1. So if I notations yk plus or yk is nothing but y at x. Okay, so at the yk denotes the approximation of y at point xk. So if we denote by y with these braces, this means exact value. And if we define this y with the suffix k, this is an approximate value, so that we can distinguish between the exact solution and approximate solution at point xk, and then we can talk about some the error part of it. And we have also seen the error in Euler's method is given by en plus 1. The at n plus 1th stage is en plus this term, which is known as this total is giving you the total error. So that this term, second term plus the last term, is known as the total error, and this the last term in the red ink is called as local discretization error. Okay, and if you so what is en plus 1 is? So if you recall, en plus 1 or en is the difference between exact value and approximate value. Okay, so this is known as discretization error, and this is local discretization error. And then we have seen, suppose if we assume that f is continuous in second variable and its partial derivative with respect to y-axis, then we can state that en, the error, is of the order of h. Okay, that we have seen in the last class. Okay, right. So so this is here. So if we assume that the f by dou y exists and continues on d, then let a second derivative exist and continues on d. Then so d is a rectangle, closed rectangle. So in a closed subset, so closed subset of a R2, closed and bounded subset of R2 is a compact set, and if the function is continuous, okay, then it is a bounded. So suppose k and m are the bounds of the second derivative of y and partial derivative of f, then we have obtained the following inequality with mod en is less than equals to ch, which states that the error remains bounded, or you can also say that large enough n it's of h. Okay, so here we have also seen that if suppose you wish to determine the error to be bounded by less than 10 to the power minus 6. Okay, so in that case you have to make h is sufficiently small. Okay, and then we have also seen that if you take h as small as possible, then there will be a round off error will be coming into the picture. Okay, and because you are going to rounding at each step, and then in totality it will be huge. Okay, so how to get rid of these things? So that's why this h need to be chosen with little care, not with very small, but it should be like, okay, in some range that we will discuss in maybe a later stage. Okay, right. So okay, so let's take one example. Okay, so find y approximation value at 0.4 by solving the following initial value problem. So we saw it is given, it is instructed that we have to use Euler's method, and with step size h equals to 0.1. So the interval a is 0 and b is this is y naught. Okay, so in interval here you can start with 0 and end with 0.4. Okay, so you can compare with the standard initial value problem, and you can extract f, x naught and y naught from the given one. Okay, so that is given by f of xy is nothing but the right hand side after writing in the simplified form y dash equals to. So here in the particular problem, this is f is nothing but minus xy square. Okay, and if you compare x naught value is 0, y naught value is 2, because these are going to be used in Euler's method. So what the Euler's method gives you is, so here noted that we are moving with the step size h equals to 0.1. So if you have x naught is 0, so what will be x1? What will be the x1 value is x naught plus h. That is equals to 0 plus 0.1, that is 0.1. Then similarly x2, that is going to be x naught plus 2h. That is going to be 0 plus 0.2h, 0.2, so that is 0.2. Then similarly x3 is 0.3 and x4 is 0.4. So to reach at x4, you need to find y1, then y2, y3, and then y4 will be the final value. Because we have seen that Euler's method is driven through the Taylor's approximation, and you know that Taylor's approximation gives you the good result in about around the neighborhood of x naught. So we can't go away from the x naught very far. So that's why we are going to look at very small interval nearer to x naught to x1, then x1 to x2 to reach to x4. Okay, so here we have taken the equidistant, so 0.1, 0.2, 0.3, 0.4. So we have to get the final value at 0.4. Okay, now, so now Euler's method is given by yk plus 1. So at any xk plus 1 point is given by yk plus h f of xk comma yk. Note that here this is an x method, because, so why we are saying this x and implicit? So explicit means because the right hand side is fully depending on the previous data, so which is already in hand. Okay, suppose it is not there, then means like right hand side also involves the value y at k plus 1, what we will do. So implicit method is the right hand side also involves the value y at k plus 1 or xk plus or y at k plus 1, then it is called as implicit method. But here it is explicit method. Okay, so yk plus 1 at any k is yk plus h time f of xk yk. Okay, substitute carefully. So function value we can replace f of xk comma yk by, you know that f of x comma y is minus x times y square. Okay, so f of xk comma yk is minus xk and yk square. So that's here replace. So we have deriven the simplified form of y at k plus 1 for Euler's method. Now you replace k equals to 0, then you will get y1. That if you replace k equals to 1, then you will get y2. And if you replace k equals to 3, then you will get y4. Okay, so what will be the values? So y at x1, y1 is equals to y naught plus h time. So you replace k equals to 0. Okay, then you substitute x naught value is 0, so there is no contribution from the second term. So y naught value is 2, so we make this. Now y at x2, y2 is equals to, replace k equals to, here this is k equals to 0, here k is equals to 1. So x1, y1 square. So now x1 is 0.1 and y1 is from here 2 values. So you have to use this value here. Okay. So using this, you have to use the value here. Okay. And then evaluate this by using calculator. So these are the final value for y2 1.96. Now use this y2 to get y3. So you are going to use this value here. Okay. Similarly, this value you are going to use here, and so on. So that final value y at x4 is going to be 1.7768. Now let's compare the exact solution. Okay, so it's a method, it's a tool which has been given, and you can use it to obtain the solution approximately. Okay, right. Now exact solution of the given equation can be obtained by using variable separable method. Okay, because y dash equals to minus xy square, so you arrange the dy with the y, function of y, and dx with x, and integrate both sides. And then initial condition gives you y at 0 equals to 2 implies c equals to 1 by 2. Replace c equals to half. So what is the y value is 2 by x square plus 1. That's going to be the exact solution. Now I have prepared one table for exact value at x equals to 0.1, x equals to 0.2, x equals to 0.3, x equals to 0.4. And then compare it with the obtained approximated value with the Euler's method. And also we have seen the absolute error in this case. So this is the first column is for this nodal points 0, 0.1, 0.2, 0.3, 0.4. Then exact value of y, it uses the formula y equals to 2 by x square plus 1. Okay, and approximate value of y, this is using Euler's method. Okay, these are the values which I have obtained. And absolute error means a mod of y at xn minus yn. The approximate value. Okay, in absolute sense. You can replace it by relative as well, divide by y, mod of y at xn. Okay, so these are the exact value which we have fixed here. Now, as exact value. These are the approximate value which we have got from the previous steps. Okay, so 2, 1.96, 1.8832, and 1.7768. And then you take the difference and take their magnitude. Okay, and you can also see that this at 0.1, the error is 0.0198. Okay, in absolute sense. Okay, so then the next is the next is 0.0369, 0.0483, 0.0527. It's monotonically increasing. Okay, but not very much increasing. Okay, it's not very much increasing. It's not worse. It's not getting worse so far. Okay, so see, it's explicitly saying this classical method, Euler's method. Okay, is there is no stability problem for these methods. These are single step methods. There is no stability problem. So there is no need to worry much about the going for convergence of this. Okay, means like error will be not very high. Okay, right. So and we will see if somewhere if there is any issue that we will mark out in during the talking about the stability problem. Okay, we will see especially for this case as well. Okay, and then we will check more or elaborate more things. Okay, right. Now this is for Euler's method, which is of order h. So like this Euler's method is derived from Taylor's approximation by truncating after second term, because means we have got the error of h square. Okay, but when you subdivide and use composite type rule, like you have done numerical quadrature formula. Okay, so similarly you have loss of 1 power of h, so that's why this O of h behaves like O of h in the interval a to b. Okay, right. So likewise we can also derive the Taylor's method of order any order now. So instead of truncate after the second term, you can truncate after the third term or fourth term or whatever higher order you require. Okay, so what is the explanation here? So here is that Taylor's algorithm for order m. Okay, so A is equals to this partition. This is uniform partition of the interval AB. And what will be the method is yk plus 1 equals to yk plus h times this. So what is this coefficient am is nothing but y dash at x plus h by 2, y second derivative, y third derivative, and so on. When we are talking about of order m, means we are truncating after the power of h to the power m. Okay, so this is looks like suppose I just want to explain how this is deriven is I'm just adding one slide here. So it's very simple to observe that see y at xk plus 1 is equals to y at xk plus h. You are looking at the neighborhood of xk only. Okay, now write down the it's Taylor's approximation, that is y at xk plus h time y dash at xk plus h square by 2 y second derivative at k plus and so on plus h to the power m by this is 2 factorial m factorial y mth derivative at k and plus that error term which is h to the power m plus 1 by m plus 1 factorial time y m plus 1th derivative at some ck where ck lies between xk and xk plus 1. So h time this, so h you can take common, that is we are denoting by observing by am. Okay, so and we are truncating after this m plus 1th term, so this is going to be the error of order h to the power m plus 1. So, okay, so this is what is happening. So you have not that y dash equals to f of xy, y at x naught equals to y naught. And if you replace m equals to 1, it will give you the Euler's method. Because Taylor's method is only driven by Taylor's method only after truncating the second term. Okay, right. So, okay, so what will be the error term? So at error term already mentioned here. This is local discretization error. Okay, so now let's so what is the drawback here? So what is the drawback here is since this is y dash equals to f of xy, so y dash can be replaced by f, then y second derivative for y second derivative you have to find the derivative of total derivative of f. For replacing y third you have to find second derivative, means implicit differentiation occurs here. So you have to proceed up to mth derivative. So you have to evaluate function values and as well its partial derivatives, all higher order partial derivatives at these points xk comma yk. So this is the payoff here. Okay, so means you are depending on the values of not only the values of f as also as on the values of its partial derivatives, higher order partial derivatives. Okay, so this will look sometimes very tedious job. Okay, so one needs to get rid of. So we will see how will we get rid of this job as well. But let's see. Okay, so let's see what will happen. So this is already we have deriven y dash equals to f of xy. You can differentiate y double dash again this and use that means like f with respect to x plus f with respect to y, because is the function of x into dy by dx. Okay, and so it is going to, so y double dash is going to be replaced by the following right hand side. Now you differentiate again once more, because you if you want to go for third order derivative as well, means like up to OH 4, OS to the power 4. So you have to differentiate this term, then you have to use here product rule, which we have simplified, and we have got the following formula that you can verify it's at your end. Okay, so then so likewise y fourth derivative, y fifth derivative if you are going for higher order. Okay, right. So likewise you have to replace these things in the Taylor's method. So this is a tedious job that we have that it can be seen very clearly. Okay, so error in Taylor's method is going to be given by En plus. Likewise in Euler's method, this is also the part of this, because y at xn is not equals to yn, there will be some round of error. So similarly at xn comma yxn, and xn comma yn will not match it. Okay, after n equals to 0. So n equal to 0, it is fine. But n equals to 1, n equals to 2, and so on, this will not match it. So this will also contribute some error. Okay, so later on we are going to ignore these things. Okay, ignore this second term. We are going to ignore this second term later on. Okay, because we are going to now only interested to minimize the local discretization error in further sessions, you guys. Okay, so this will be the error expression for the Taylor's method of order n. So solve the previous problem using Taylor's method of order 2. So then what will happen is, so then this is the Taylor's method, which is nothing but AK. Sorry, this is not AK here. Let me write it specifically. This is A2. A2. Okay, right. And this is A. Okay, right. So what is here is yk plus 1 is equals to yk plus h time a2 xk comma yk. So what is a2 xk comma yk? If you look at that, this is nothing but y at x, y dash at xk plus h by 2 y double dash at x. Now see, y double dash is going to be, we are replacing it by f dash. Okay, means it's total derivative. Dash means dash stands for here is total derivative. Okay, and error is going to be h cube by 3 factorial. You can get previous session. Oh, sorry, previous previous slide, and you can find out that error is nothing but O of h cube. Okay, so to replace these terms, you have the replacement of this straightforward. Okay, because from the problem itself. But for replacement of this term, you need to differentiate, and then you have to replace at point xk comma yk. Okay, so this is what is happening. So this is given that y dash equals to f of xy. Then you need y double dash for f dash, so which we have derived here. So if you simplify it, it's going to be going by this. So fx plus fy into f. So partial derivative, you know how to obtain, and you can use there. Okay, this here to this. Now replace the terms carefully. So f of xk comma yk is minus xk yk square. So f dash at xk comma yk is replace x by xk and y by yk here. So that is 2xk square yk cube minus yk square. Okay. Right. So now we are going to compare the values at the different points of means obtained here. Okay, with the previous values which was obtained by using Euler's method. Okay, so we go for k equals to 0, then we will get y1. K equals to 1 will give you y2. K equals to 2 will give you y3, and so on. K equals to 3 will give you y4. So we are going to substitute. So h, not that h value is 0.1. Okay, and x naught, x1, x2, x3, x4 are 0.1, 0.2, 0, 0.1, 0.2, 0.3, 0.4 respectively. Okay, and then you will obtain this yk values as well. Okay, so if you fix all the values here, so you are going to see that approximate value of y. So from the first step onwards, so previously, if you recall from the Euler's method, okay, from the Euler's method, if you compare Euler's method values was here was 2, exact value was 2, and here also was 2. Okay, so for order h, and the values is 1.96, 1.8832. So 1.96, 1.8832, and 1.7768. Okay, so these were the values given by Euler's method, which is of order h. Now we have increased one order, so it is 1.9802, it is 1.98. So 1.9231, it is 1.922. So you can look at the error now. Okay, so it is closer. So of h square, it's far. Similarly, here also for the fourth step, this is also far. Okay, so this is a better approximation. You can increase the order now more. Okay, by using Taylor's method. Okay, and if you increase, you will get more higher accuracy. Okay, but what is the payoff here is you need to find higher order derivative. Suppose you are going to involve third order derivative, then you have to find the third order, all the possible, you can say, all the possible. So for second order, you require first order partial derivative. For the third order, you require all the first order and second order partial derivatives at the different values. Okay, and so on. So this is a tedious job. So likewise, you can extend. Okay, right. Now we are going to look for its equivalent substitution, you can say, or in other words, we don't wish to go for finding the partial derivatives of f, or we are only wish to stick with the evaluation of the function only. Okay, so means you are going to give me the function. I will take the help of the function only, and then I will try to approximate the solution with good accuracy. Okay, so here I will be deriving the Runge-Kutta method of order 2. Okay, and how it will be derived is we are going to see here. Then at the end, means after derivation of this, so we will give you the stepwise how this method is derived. Okay, then we will directly state the Runge-Kutta method of order 4. Okay, so now note that the Taylor's method gives you y at xn plus 1 is going to be, if you expand it by using the Taylor series, till of h4. Okay, now what we wish to here is we want to derive derive a scheme which is like yn plus 1 equals to yn plus a time k1 plus b time k2, and where k1 is h time f of xn comma yn and k2 is h of f xn plus alpha h comma yn plus beta k. Means you are moving in the direction of h comma k1, you can say, from the point xn comma yn. Okay, means in some direction here. So okay, and then you are going to take some average or mean or whatever these slope values, you can say. So you have 2 points xn comma yn and 2 points xn plus alpha h comma yn plus beta k. Okay, so k1 is nothing but this here. So what is here is, so Runge-Kutta method suggests is you substitute this k1 and k2 here and try to match. Okay, try to match with the equation 1 for as high degree as possible. Okay, for power of h. So like this is simple. So f at xn comma yn, we can't do anything with it. See, this is f of xn yn. This is going to be y dash at xn. Okay, now for this, what we are going to do is we are going to use the Taylor's approximation. Okay, so Taylor's approximation in 2 variables. We are going to use this and then substitute back here, and then we will try to compare it. Okay, so now that we are going to look at. So if you recall, what is the Taylor's approximation in 2 variable is f of xn plus h comma yn plus k, or x plus h comma y plus k is equals to f of xy plus h time dou by dou x plus k time dou by dou y f at x comma y plus 1 by 2 factorial h time dou by dou x plus k time dou by dou y square f at x comma y plus and so on. Note that these are the operators. Okay, square means they are operating on each 2 times. Okay, so similarly this. Okay, and if you open it up, you will get the learned your approximation. Okay, maybe you have learned in the same fashion in your calculus classes. Okay, so or you can use your notations, okay, from your notes, and you can replace the terms here according to your notes. Okay, right. So now if you replace x by xn plus alpha h and y by yn plus beta k1, then what we will get is, we wish to determine a, b, alpha and beta such that equation 2 agrees with equation 1 for highest possible order. So we will use the Taylor's approximation of functions of two variables to expand this. Okay, right. So Taylor's approximation of this is going to be given by f at xn comma yn at this point plus, so h time dou by dou x plus k time dou by dou y. So h is alpha h here and k is beta k1 here in this case, dou by dou y of this plus 1 by 2 factorial the square of this term and f at xn comma yn plus of h cube. So we have stopped after the second term because we want to go for RK method of order 2. Okay, so we are not going more than h cube here. Okay, now if you expand this, the first term as it is, second term alpha h time dou by dou x of this at xn comma yn, so fx at xn yn plus beta k1 time fy at xn comma yn. Just substitute carefully. Here, so what is a plus b whole square? So not that this alpha h and beta k1, they are treated as a constant only. Okay, right? So it is like this square plus this square means a plus b whole square if you open. So a square plus b square plus 2 times alpha h into beta k1 time dou square by dou x dou y. Okay, so likewise we are going to explain. Okay, so operator is operate on only. Okay, it's not like dou by dou x of beta k1 time dou by dou y is beta k1 is out. Okay, similarly that. Okay, so treat these alpha h and beta k1 as constants for opening these powers. Okay, right. So alpha h whole square dou square by dou x square plus beta square k1 square dou square by dou y square plus 2 times alpha h into beta k1 dou square by dou x dou y. So then if you multiply by 1 by 2 inside, what you will get is alpha h whole square by 2 fxx at xn yn plus 2 will get cancelled here, alpha time beta time h time k1 f at xy xn comma yn. So here we are using the fact that mixed derivative theorem is applicable. Means all the first order and second order partial derivatives are exist and continuous. So therefore fxy and fyx both are the same thing. Okay, so plus the next term is beta k1 whole square by 2 times this and plus OHQ. Now we will try to match. Okay, right. Now substitute. So now yn plus 1 is equals to yn plus ak1 plus bk2. So if you substitute, so yn plus a time k1. K1 is h time f of x and yn. Okay, so if you recall, k1 is h time f of xn comma yn. So the first yn plus ah f of x and yn. Okay, now second term b time k2. So k2 is h time f of xn plus alpha h comma yn plus beta k1. Now note that k2 also have h here. So when you take h inside of the expansion, so if you multiply by here, so here h will come, here h square beta k1. K1 is also having h, already having h. So one more h is there, so h square term. So this will be h cube term. This will be h here. K1 is also having h. So h square here, h square into h is h cube. Similarly here h. These are h cube and this is OH4. Okay, now multiply by h and then b. So bh. So bh f of xn comma yn. So f of xn comma yn. So that is going to be adjust with this second term. Ah f of x and yn plus bh f of x and yn. That is going to be plus b times h f of x and y. Plus Now, if you look at here, so alpha b h square fx plus beta b h f, right? K1 is h time f. Okay, so h square is there, so h square out, b is out. Okay, so b h square alpha time fx plus beta time fy time f at x and yn. Similarly, for the rest of the term that you can write down, simplify, replace k1 by h time f here. Okay, and multiply by b time h. Okay, and then you find out these terms of bh cube will be out. So then you have alpha square by 2 plus alpha beta plus beta square by 2. So here one f will be there because k1 is there. Here k1 square was there, so it is f square is coming at x and y. And this term is of order h to the power 4. Now, if you compare with the Taylor's approximation, so because Taylor's approximation gives you y at xn plus 1 equals to y at xn plus h is equals to y at xn. So you open up, then replace the y dash by f of x and yn, y double dash by fx plus fy time f that we have already derived. Y third derivative also we have derived, that is also replaced. Now compare with these two expression on the right side. Now, so first term we are telling that we are going to assume that y at xn and yn are the same. Okay, so we are ignoring the fact that y at xn and yn may be different. Okay, so we are not interested in this. Okay, we are interested in the discretization error to be as small as possible. So we are not distinguishing between y at xn and yn onwards. So now if you compare, so y at xn and yn are the same, the first term matches. Now if you go with the second term, the second term will match if and only if a plus b is 1. So one condition is getting is a plus b is 1. Now second term here, so second term will match when? So when you have b is equals to 1 by 2, alpha and equals to beta, right? Or alpha time b, right? So if you take b inside, okay, so alpha time b and beta time b are equals to 1 by 2. Okay, so that these are two more conditions there. So 3 conditions in 4 constants. Okay, so far. Now, likewise, try to compare this. Okay, the third term. Okay, now if you are going to compare the third term, they are not going to be comparable. Why? Because this is here only involving fxx, fxy, and fyy. Okay, whereas in this approximation, it also includes fx into fy, fy square, f. So no matter what value of alpha beta you choose, it will never match to this term. So you have to truncate after this here. Okay, right. So you can't match with this because here it also having first order partial derivative, but in the above approximation it is not there. Okay, so you have three condition in 4 unknowns, means you have 1 degree of freedom. Okay, so one constant you can choose arbitrarily. So alpha a plus b equals to 1, b time alpha is 1 by 2, beta equals to 1. So what RK2 does is it is using the symmetric point. Okay, symmetric with respect to midpoint, you can say. So a equals to b equals to 1 by 2 and alpha equals to beta equals to 1. So that we have that also is chosen by RK2. So if you fix a value is 1 by 2, b value is 1 by 2, alpha and beta values are 1, then the things are going to be, the method is going to be known as RK method of order 2. Okay, right. So is the RK method of order 2 is yn plus 1 equals to yn plus 1 by 2 times k1 plus k2. So a is 1 by 2, b is 1 by 2, so replace. K1 is specifically h time f of x and yn, and k2 is h time f of xn plus alpha is 1, comma yn plus beta time k1, so beta is 1. Okay, so alpha and beta are value 1. So let's fix it up. Okay, right. Now you can talk about the error term. Okay, so error is given by y. So that take the difference between y at xn plus 1 and yn approximation. So if you take the difference of these two, so y at xn plus 1 minus yn plus 1. So till this terms all are get cancelled. So the first, second, and third, fourth. Okay, so first, second, this third term. All these three terms will get cancelled because we have matched it with this one. Okay. Now what is going to be this? This term will survive. Okay, the last two terms here and last two terms here, and then take the difference of them. Okay, so that will give you the error here. So that if you take LCM and all, so the error expression is going to be given by this. And so it is going to be O of HQ in particular. Okay, so you have not got O of H4. Okay, right. So let's do, let's state the Runge-Kutta method of order 4 now. Okay, so since you can extend in the similar way. Okay, so instead of K1 and K2, you can go for K3 and K4, 2 more points you will add. Okay, and then you try to match with the as high degree as possible. Okay, so the method is similar, but it will be very lengthy. So we are not going to accommodate those messy things here. Okay, so we are going to directly state the Runge-Kutta method of order 4. Okay, so that is given by, so here is this, it is stated now. So yn plus 1 equals to yn plus 1 by 6 times. So now one more thing is there, you can look at. So 1 plus 2 plus 2 plus 2, 1. They are 6. 6 by 6 is 1. So in the RK2, you have 1 plus 1 is 2, right? So RK2, if you see the sum of the weights for K1 and K2 is 2 by 2, that is 1. Okay. So similarly, you can also see that if you go for RK method of order 6 or higher order, okay, then it will also, the weights sum is going to be similar as which you are going to divide here. 1 by 6 times the summation will also be 6 here. The further also you will see the similar type of results here. Okay, so here K1, K2, K3 and K4 are explicitly given here. So K1 is similar h time f of xn comma yn. Then K2 is h time f of xn plus h by 2 comma yn plus K1 by 2. So this is using the previous value. Okay, this is using the previous value and this is using this one. Means you are stepping half step ahead, you can say. Okay, means 2 times, these are like half step ahead. Okay, fixing xn comma yn, and you are going to xn plus h by 2 comma yn plus K1 by 2. Okay, right. Similarly, so then you again at the same point, but you are going to go for yn plus K2 by 2. So you are going to use this. Similarly here xn plus h comma yn plus k. And you will see the local discretization error in this case is of O of h5. Okay, so we are not writing here explicitly what will be the exact form of the error term. So, but it is going to be of h to the power 5. Okay, now let's look at the example. Okay, then we are going to solve the previous problem using RK4. So we have skipped the RK2 because it is matches with the RK2 is matches with the Taylor's method of order 2, and it is going to give you the same value because you have matches in the same. Okay, only the advantage in RK2 is that you are going to stick with the only function evaluation. Okay, so that is a big advantage here. So instead of going for partial derivatives, they are not simple to evaluate. Okay, they are not, the f is having a very simplified form which you can differentiate as many times and you can get the very simple form. If it is not the case, then our Taylor's method of order 2 is giving you the very tedious job. Instead, you are going to work with the RK2. So it is better to work with RK2 because it requires only from 2 function evaluation. Okay, and so on. So RK2 is better than our Taylor's method of order 2 in that sense. If the f is not, means f is not in complicated form to differentiate. Okay, so we are going to solve the previous problem using RK4 now. Okay, so we are just fitting all the things carefully here. So yn plus 1 equals to yn plus 1 by 6 times this expression here. So what are those k1 and k2, k3, k4? They are similarly copied from the previous slide. Now, note that in the problem, what was there is f of x comma y was minus x times y square. Now replace f of xn comma yn by xn yn square. Xn plus h by 2 comma yn plus k1 by 2 f at this point is xn plus h by 2 into yn plus k1 by 2 whole square, and so on. Now n equals to 0. Okay, for n equals to 0, y1 equals to y0 plus 1 by 6 times this. So here replace n by 0. So f at x0 y0, h f at x0 plus h by 2 comma y0 plus k1 by 2, and so on. And then replace corresponding values. Recall that x0 is 0, x1 is 0.1, x2 is 0.2, okay, and so on. Okay, right, and h is 0.1, recall from the previous, and y0 is 2. So we are recalling from the previous problem. So if we are going to do that, so k1 value is obtained 0, k2 value is minus 0.02, k3 value simplified by using the calculator. So minus 0.01A98, k4 is this. And then if you substitute, it is 1.9802. This is exactly matches with the 4 decimal places. Okay. Now, similarly for n equals to 1, you are going to get the values of k1, k2, k3, k4. Okay, x1, y1 square, x1, so replace xn by 1 there on the right side now, similarly. Then if you update the y2, this is going to be exactly matching till 4 decimal places. Okay, so this is a, you can say, the RK4 methods. So the rest of the things also you can verify that they are going to be matching exactly with the, at the 0.3 and 0.4. Okay, so this gives you the very better approximation. What is other advantage is that it involves only function evaluation. It not involves the derivative values. It's going to only involve the function values at the different points. Okay, right. So total number of function evaluation here is 4. Okay, so right. So this is RK4. Right. Now, so see, these are classical methods. There is no stability problem here in the these methods. Okay, so likewise we can proceed for now is using the numerical integration formulas. Okay, so we have, here we are, so we have the given initial value problem. Okay, so let's have given initial value problem, and you have the uniform partition. And then we integrate 1 with respect to x on sub interval xi to xi plus 1 we get. So that is another approach, okay, you can say, to obtain the already derived method, and we can further develop new methods which are predictor character methods. Okay, so now we have only obtained a single step methods. Okay, so you have obtained a single step method. You give me the point x0 value, y0 value, a function, then use RK4 or RK2 or Euler's method directly. You can just run the program and you can approximate. Okay, they are single step methods. Okay, that's not a problem. Okay, now we are going to use the predictor character. Means these single step methods are also known as predictor methods. Okay, so these methods are also called predictor methods. Now, how will you correct the values? Okay, so these also, so because correcting also will take the place and will give you the more accurate value than the previous value, correct predictive value. So that's how it will be possible. So that we are going to look at now. Okay, so numerical integration. So suppose everything is fine with the problem. Okay, means it is possible to integrate and everything is there, means you can do integration both sides and you can find the equivalent integral equation. So if you integrate 1 with respect to x on the subinterval xi to xi plus 1, what you will get? So integrate both sides, xi to xi plus 1. So y dash will be integrated by y. And y at xi plus 1 minus y at xi is equals to integration xi to xi plus 1 f of x comma y is dx. Right? So far everything is fine. Okay. Now, what is next is, now see, y is function of x and a function is, f is a function of x and y, but y is also depends on x. So you can treat this complete f function as a function of x only, let's say. Okay, for time being. So then later on, means you can recall the definition, what is f of x. So we can be treated as a function of x, since y is a function of x. You can treat completely as a function of x. Y is unknown. So you cannot directly integrate the right side. Okay, the integral you cannot evaluate because y is unknown. So what you will do? So what you will do is, we are going to use interpolating technique for getting approximation of integers. So what are the interpolation technique we have learned? We have learned the rectangle rule, we have learned the midpoint rule, we have learned the trapezoidal rule, Simpson's rule, and Hermite interpolation, and so on. Okay, those things can be fitted also here. Okay, so what will be happening if you go for, let's suppose, rectangle rule. Okay, so rectangle rule tells you that you are going to integrate this integral by the length, so by using the rectangles. Okay, so if you have this is going to be, if you replace by this is f of x. So this integral is approximated by h time f of x, f of xi. So at the left hand point, what we have tried to match, okay, in the rectangles, in the rectangle rule. Okay, so you can choose either left hand point or right hand point. Okay, it doesn't matter, because in the limiting case, it is going to converge the integral value only. Okay, so the approximation of this integral can be replaced by h time f of xi. What is f of xi is small f at xi comma y at xi. And now if you look at the formula shape, it is nothing but the, it's nothing but the Euler's method you will get. Okay, so what I have done is, let's see, so if you go for rectangle rule, means f of x is approximated by a 0-degree polynomial. Okay, 0-degree interpolating polynomial by using the data xi comma f of xi. Okay, so f of xi plus f of xi comma x by Newton's polynomial, and you replace. Okay, and then error also can be derived in a similar form. So the integral on the right side can be replaced by this formula h at f of xi when you use the rectangle rule. Okay, and the error, what it will be, the error in this term here is h square by 2 times f dash at ci, capital F dash. So what is capital F dash is small f dash, means small f dash. What is small f is y dash. So it is going to be y double dash at ci. Okay, likewise you can replace these things here. Okay, right. So once you use this, so what you are going to have is, so now if you substitute in the above equation, you can say 2, that y at xi plus 1 is approximated by y at xi plus h time f of xi. Replace f of xi by small f. So small f at this. So h square by 2 f dash at xi. So that is going to be y second derivative at x, and which is nothing but the Euler's method, what you have got. Right? Okay. Now, instead of rectangle, now we are going to use the trapezoidal rule. Okay, so trapezoidal rule, what it does is, trapezoidal rule interpolate this capital F by an interpolating polynomial of degree 1 by using xi and xi plus 1. Okay, right. So their question comes, how will you predict the value of y at xi plus 1? Okay, so that we are going to see now. Okay, so we were solving the following initial value problem. So likewise, we have divided the interval in n subintervals which are equivalent. Okay, and points are equidistant. Okay, now integrating 1 over the sum interval, we have the following formula. Okay, where f of x is f of x comma y. Now trapezoidal rule implies what? Y at xi plus 1, y at xi, the first term is plus. So this is going to be approximated value. Okay, so plus h by 2 times f of xi plus f of xi plus 1. So if you recall, f of a plus f of b divided by into b minus a by b minus a into f of a plus f of b by 2. Okay, so that is the area of trapezium. Okay, so this is so between the point xi to xi plus 1. Okay, right. So if you look at here, so this is your xi, this is your xi plus 1, and you have let's say this is there, and this is the trapezium. So this is, let's say, f of x, this is f of xi, this is f of xi plus 1. Then you know that is the area of trapezium is xi plus 1 minus xi times f of xi plus 1 plus f of xi by 2. So but xi plus 1 minus xi is h, so h by 2 times this. Now this will be coming out as an implicit method now. It's not an explicit. If you look at the right hand side carefully, okay, if you look at the right hand side carefully and look at this term. This term involves the value of y at xi plus 1. But we are not ready with this. So what do you have to do? Okay, so this we are known as character formula. Why it is so? Because you have to find out first y at xi plus 1 now by using some of the single step method. Okay, that we will call as predictor formula. Okay, and then we are going to correct it by looking at the iterations values here. So this is also called character formula. Okay, not only single, so it's one of the character formula you can. Okay, you can correct the value at y at I plus 1. How? Let's look at, this is going to be, which is also called, this is also known as Euler's modified method. Okay, this is also called Euler's modified method. Okay, so now, so in order to use Euler's modified method or trapezoidal rule, we will proceed as follows. So fix xi, okay, and define zeroth iteration. Zeroth value, you can use we have used here Euler's method. You can use Taylor's method as well. It's not a Taylor's method of order 2 or RK2 or RK4. Okay, but when you combine Euler's method with trapezoidal rule, then it is known as Euler's modified method. That's what it is, because we are using Euler's method for predicting the values. So this is a predictor. Okay, so yi plus 1, so zeroth approximation can be obtained by Euler's method. Then yi plus 1 can be obtained replacing the right hand side. In the right hand side, you replace the value yi plus 1, the zeroth approximation. Now, second step, if you are going to with 2, yi plus 1, 2, then everything will be remaining same. Only you are going to replace yi plus 1 by now new approximation, which you can treat as better approximation. Now, question is how much we have to go for it. Okay, or what will be the stopping criteria? Okay, so stopping criteria you can place, you can decide what the desired accuracy by defining some error tolerance. Okay, and then you can obtain the relative error and make it less than epsilon, and then you can make the loop out. Okay, so sometimes what happen is, suppose you have given the number of iteration, maximum number of iteration is, let's say, is equals to 100. Let's say 100 number of iterations you are giving. But still, this error tolerance is not satisfying. What you will do in that case? In that case, what you have to do is you have to go back and reduce h by 2. Okay, and then you work. Now still it is not, you reduce by h by 4 then, and so on. Okay, so but in general what happen is, so if you choose h properly, means carefully, okay, then 1 or 2 one or two iterations are sufficient here. Okay, once you choose H properly. Okay, so right now, so Euler's method is explicit and can be called as a predictor formula, and trapezoidal or Euler's modified rule is implicit and character formula, which correct the values from the Euler's method. Generally, character formula is more accurate than predictor formula. Okay, right. So error in Euler's modified method, that is given by the trapezoidal rule. What we have learnt there was minus h cube by 12 f double dash at di, but f double dash is my third derivative at di. That is driven from similarly as we have done in numerical integration case. Okay, so di lies between xi and xi plus. Right. So now, if we are going to solve the previous problem again, okay, approximate y at point 2 using Euler's modified method with step size h equals to 0.1. So I have specifically mentioned here h equals to 0.1, x naught is 0, y naught is 2, x1 is x naught plus h 0.1, x2 is x naught plus 2h 0.2. Then we have started with the 0th approximation because we are going to use Euler's modified method. So Euler's modified method suggests that you have to use 0th approximation using Euler's method. So y1 as 0 is y naught plus h times f of x naught y naught. Now carefully you substitute the value. So y naught is 2, h is 0.1, and f of x naught y naught, f of xy is minus x times y square. So minus x naught times y naught square. So replace x naught by 0 and y naught by 2. That's what you will get is 2. So that is a predicted value. Now we use the Euler's modified method. Okay, so y, which is given by, for y1 case, y1 k plus 1 is equals to y plus h by 2 times this. Okay, f of x naught y naught plus f of x1 common k. So replace k equals to 0. What you will get is y1 0 here, and replace f of xy by minus xy square. So and then you replace here the carefully the value of y1 0 by previously 2. Okay, and simplify the things, you will get 1.9. Now for k equals to 1, so everything, every term is same, only change is here. So that is going to be y1 1. So y1 1 is going to be 1.98. So y1 0 was the previous one. Then you will see this 1.9803, how much close it is. So within 2 iteration, okay, we have arrived this. Okay, now so therefore we are going to call this is a final of y. Okay, 1.9803. Now then y1 then is fixed now. So now then you go for y2 at 0th approximation by using Euler's method. Carefully substitute all the values. So this is a predictor one. Okay, this is a predictor value, predicted value. Okay, then we are going to correct it by using the Euler's modified method. So here you are going to replace the new approximations. Okay, right. So for k equals to 0, substitute the value y2 at 0, and then you obtain this 1.9230. And you know, see how much close it is. 9231 was the exact value. Now for k equals to 2, k equals to 1, it is still means waiting, means like going around only 1.9231. So y1 plus h by 2, here you are replacing the new approximation here, and then you will obtain the final. So that you will call as final value of y2, that we will call as y2. You can go with one more step, okay, but you will still surrounding with this one. Okay, then you can go for y3 in the similar fashion, you can go for y4 and so on. So this is by using the predictor corrector method for the above problem. So, but what is the disadvantage of predictor corrector method is there is a stability with that. Okay, so that we are going to check with the in the end time. Okay, what is the next we're going to look at is midpoint rule. So we have seen in the numerical quadrature formula, okay, how this midpoint rule behaves. So if you interpolate a 0-degree polynomial, you are going to get a numerical quadrature which is going to be exact for polynomial of degree less than equal to 1. Okay, so that we have already seen. Here, so similarly, so now we are going to midpoint rule. Okay, we are going to use the midpoints. So you have the nodal points are what? What are the points are x naught less than x1 less than x2 less than x3 on less than xn, or xn minus 2 less than xn minus 1 less than x. So what you have to do? So instead of introducing one more nodal point, what we are going to take is we are going to choose the interval x0 to x2, x2 to x4, xn minus 2 to xn. Okay, and take this x1, x2, xn, this x1, x3, and this xn minus 1 are the midpoints of this because they are equidistant. Okay, so that is why we are going to integrate on this interval xi minus 1 to xi plus 1. Then what we get is xi plus 1 minus y at xi minus 1 is approximated by, so xi plus 1 minus xi. So you are, what was the formula? If you recall, what was the formula for the integration? Is b minus a, integration a to b f of x dx is approximated by b minus a times f of a plus b by 2. So xi plus 1 minus xi minus 1, that is, and f at xi plus 1 plus xi minus 1 divided by 2, that is nothing but xi point. So 2, what is that? Is 2h times f of xi comma yx. Okay, whose error term also in the similar fashion. So f second derivative was, but f second derivative but y third derivative at di is h cubed by 3. Now look at this. So this is y plus 1 is equals to yi minus 1 plus 2h f of xi comma y. Now what will happen? Can't go for I equals to 0 here. Why? Because I equals to 0, y1 equals to y minus 1 plus 2h times f of x naught comma. So you don't know what is the y minus 1. Okay, so we will state for I equals to 1. But for I equals to 1, so y2, what is the y1 plus 2h times f of x naught comma y naught. So we have accept the y1 value. So what we will do is we are going to approximate y1, okay, by using one of the single step method, Euler's method or RK method of order 4 or 2, or Taylor's method of order any higher order we can use here to get y1. So it is not self-starting method. Okay, so you need to start with some single step method, then it is fine. So let's take one. So here we have what we have stated. For approximating y1, we require y0 and y minus. So however, we are only having y0 to start. So therefore, one needs to approximate y1 by the explicit method. You can use Euler's method, RK2, RK4, etc. And then approximate y2 using midpoint. So let's use it and problem. Okay, so midpoint rule says that y2 is, so we want 8.2, and your partition was 0 then 0.1 less than 0.2. So this is your xi minus 1, this is xi plus 1, this is your x, means x0, x1, x2. Okay, so instead of integrating x1, we are integrating x0 to x2, and then we are trying to identify. So y2 equals to y plus 2h times f of x1 comma y1, right? I equals to 1. So we have x0 value, we have x1 value, we have x2 value, we have y0 value, we have h value, we have f definition, but we don't have y1. So to get a y1, but in order to find y2, we first find y1 using the method. So we will use arc. So we have already used RK4. Okay, so RK gives you y1 was given that y1 value is 1.98028. We have already derived the previous problem by using RK4. So we are just grabbing one y1 value from. So y1 is 1.980. Okay, now if you try to do, that is going to be, if you substitute fully the values, it is going to be 1.9216, which is more accurate than the Euler's method, right? Which is more accurate than the Euler's method, because right to 1.9231. Okay, right. Now, but there, as I mentioned, there is always a stability issue with these type of methods which are not self-starting. Okay, so let's see one example. Okay, so let's have this one problem: y dash equals to minus 2y plus 1 with 0 initial value is y at 0 equals to 1, whose exact solution can be obtained by using the method, or this is a standard linear differential equation of first order. You can find out the integrating factor and you can write down the solution directly. And the integral is considered, interval is considered to be AB is equals to 0 to 4. And so this example is taken by the book by Conte de Boer, which obtained the solution of this problem over the interval 0 to 4 with step size h equals to 1 by 32. He obtained the solution by using Euler's method and by using midpoint rule. Okay, and try to compare between the error terms. So some of the selected values of this, so you can perform the Euler's method and midpoint rule. So then you can look at the errors of the at different points, with some of the selected points at xn with Euler and midpoint. Okay, these are the errors, comparison of errors, not in absolute sense. Okay, it's not in absolute directly y at xn minus y. So you can see this is Euler's method is minus 0.00590, 0.00427, 0.0023. It's monotonically decreasing. Error is decreasing monotonically. Right. Now, if you look at the midpoint at 0.5, it is better. It is better than Euler's. For at 0, it is still better. Now at 1.5, it is also okay. But when you have at 3 point, it is worse. Okay. If you go with the at 4, you will see it is more worse than the Euler. So there is a stability issue with the midpoint rule. So it is not monotonically increasing. It's something suddenly it is increased now, right? Increasing on. Okay, right. So how do we check the stability issues now for the each method? We are going to look at, okay, in the next final session. Okay, and then we will state the application to boundary value problem in the next session. So here we are going to close now.